All right, the question we have on the screen here says an electron of mass 9.1 times 10 raised to power minus 31 kilogram moves with a velocity of 4.2 times 10 raised to power minus 7 meters per second between the cathode and the anode of an X-ray tube. Calculate the wavelength. Now take Planck's constant, H, equal to 6.6 times 10 raised to power minus 34 joule seconds. So to solve this question, just like I said, for every physics question, you have to start by listing out your parameters. When you write them out, an electron of mass, so you write the mass of the electron is equal to 9.1 times 10 raised to power minus 31 kilogram. Moves with a velocity, they give us the velocity of the electron, which is equal to 4.2 times 10 raised to power minus 7 kilogram. Sorry, meters per second. Okay, they say we should calculate the wavelength. You know the wavelength? The symbol for wavelength is lambda. Lambda is what we are calculating. And we are given Planck's constant. The symbol for Planck's constant is H. Planck's constant is equal to 6.6 times 10 raised to power minus 34 joule seconds. Okay, now how do we solve this kind of question? How do we solve this question? So you remember that according to the Planck's constant, we have it that, according to the Einstein's formula, for photoelectrons, we have it that E is equal to HF, where E here represents energy of light. So when this energy, they are moving, an electron has a mass and moves with this velocity, so this V is the velocity of the electron. You also remember that this formula E is also equal to half mv squared. Okay, half mv squared. Then you also remember that wavelength, according to de Broglie, wavelength is equal to h all over mv. Yes, lambda is equal to h all over mv. So with this, I think we use this formula. This formula is not about energy, because the reason why we can't use this formula, we can't use this, is because this is about the energy of the electron. And remember that this is the energy, not the energy of the electron, please. This is the energy of the light that is incident on the metal, okay? The energy of the electron should be the kinetic energy, which is half mv squared. But nothing was said about energy here. So the formula to use here would be this de Broglie's formula. So according to de Broglie, lambda is equal to h. H was given as 6.6 times 10 raised to power minus 34 divided by mass was given as 9.1 times 10 raised to power minus 31 times the velocity of the electron was given as 4.2 times 10 raised to power minus 7. Okay, so we work this out. So lambda here is equal to, get our calculator. To work this out, we're going to have it that, first of all, okay, can do everything together. So we'll have it that 6.6 times 10 raised to power minus 34, okay, divided by open bracket, 9.1 times 10 raised to power minus 31 times 4.2 times 10 raised to power minus 7. Close the bracket and press equal to. So my answer here is equal to 1,726.8 meters. So that will be the value of the wavelength. All right, what you get. So we move to the next question. The next question here says, state 3 conclusions that can be drawn from Rutherford's experiment on scattering of alpha particles by a thin metal foil in relation to the structure of the atom. Okay, you know, there's what we call the atomic theory or the atomic models or the model of atoms. Now, during the discovery of atom, so many theories, so many statements were made by different scientists. It started with John Dalton. From John Dalton, it moved to Thomson, J.J. Thomson. And from Thomson, it moved to Ernest Rutherford. From Rutherford to Bohr, the Bohr. And then we now have what we call the modern or the quantum theory. Okay, so, you know, the Dalton discovered the atom itself, but, you know, he made a particular statement that atom is an indivisible particle of a particular substance, which means that atom contains nothing inside, it cannot be divided again. So this was further explained by Thomson, who discovered that the atom is made up of a cloud of positive structure, or a cloud of positive gas that you have some negative particles or negative charges embedded inside, just like you have the watermelon. The flesh, that red part of it being the positive, and then the seeds representing the negative. So he discovered that this atom has something inside. It is not indivisible. But there are so many things he could not explain. He could not even explain the location of the nucleus. Now, this man called Rutherford now made an experiment with his students. So he made an experiment, and look at what he did. Now, since this man said, yes, that there are some electrons inside of a positively clouded atom, you know, he used a gold foil. So since every matter now has atom, so he used a gold foil, and this gold foil, you know, he casted an alpha ray on this gold foil to observe, to see what will happen. So he sent an alpha ray on a gold foil. Let's say this would be the gold foil, for example, and this would be the alpha ray source. So he scattered some alpha rays on this gold foil. You know, he discovered something. One, in fact, from his discovery, you know, he was able to make, you know, conclusions about this particular experiment. I said, this is an alpha particle. An alpha particle is positively charged. Alpha particle represents a helium atom with mass number of 4 and atomic number of 2. So when he projected this alpha particle on this, he discovered 3 things. One, he discovered that most of these rays pass through the atom. Most of them, or many, pass through. That's one. Number two, he discovered that some of them, on getting to a particular point, they deflected. Some of them, no, on getting closer to a particular point, they deflected. So some deflected, and that's number one. I said number one, he discovered that most of them passed through. One. Two, he discovered that some of them deflected. And three, he discovered that few of them few of them bounced back. That few of them bounced back. So one, his discovery, most or many pass through undeflected. They just pass through. And he made a conclusion. With that, if many will pass through, it shows that nothing is stopping them. So it shows that this atom is mostly empty. So, first of all, Ernest Rutherford discovered that the atom is mostly empty. That is why many of these rays will pass through without deflection. The number two, the ones that changed direction, that deflected, he said, what could make this alpha ray deflect? It means that there's a charge here. Since the alpha ray is positively charged, so it is only positive that will push away positive. So he said, it means that this nucleus inside here is positively charged. That is why it's pushed this positively charged alpha away. So he now said he discovered from this so that the nucleus is positively charged, or a positively atom consists of positively charged nucleus. The atom is made of positively charged nucleus. That's number two. The number three, those ones that bounce back, what does it signify? Now we'll get something like a tennis ball or a tennis ball, and I throw it on a cotton, on a cloth, this cloth here. If I throw it on this cloth, it just hits and falls. But when you throw this on a wall, the tennis ball on a wall, it bounces back, telling you that this wall is more dense than the cloth. Okay, it's harder than the cloth. Therefore, the density of the wall is greater than the density of this cloth. So with this man said, if these rays will bounce back, it means that the nucleus is heavily dense. So, number three, he discovered that the atom is made of heavily dense nucleus. So it was this man that discovered the nucleus and gave a proper explanation about the nucleus. He discovered that the nucleus is positively charged. He discovered that the nucleus is heavily dense, and the surrounding of the nucleus is empty. So these are the conclusions made by Ernest Rutherford during the atomic models of the theory. Sure you get. All right. Okay. So the next question here believe you can see. It says, the diagram below illustrates the energy levels of an electron in an atom. If an excited electron moves from N2 to NO, calculate number 1, frequency. Number 2, wavelength of the emitted radiation. Then we are given the Planck's constant, H, equal to 6.6 times 10 raised to power minus 3, and 1 electron volt. That is, electron volt is equivalent to 1.6 times 10 raised to power minus 19 joule. C here represents the speed of light in vacuum, is equal to 3 times 10 raised to power 8. And this is WAEC 2010, number 15, theory question. All right? So to solve this question first, this is about the energy level. Remember near Bohr, the Bohr's atomic model. Now, because Rutherford could not explain the energy levels of the electrons. Okay, so Bohr, added his own theory to explain the energy levels, saying that these electrons, they are not just fixed. And with the way Rutherford made the statement, it is possible that an electron can lose energy, and will now be trapped in the nucleus. So Bohr, explained that these electrons in the shell of an atom, that they are arranged according to their energy levels. Now, one electron can gain energy and be excited. When they are excited, it means that they have jumped from a lower energy level to a higher energy level. Still, an electron that is excited already can lose energy. And when it loses its energy, it will be de-excited. De-excited means that it is going to drop in that energy level. That is from the higher energy level to the lower energy level. So these lines we are seeing here represent the energy levels. NO, that is the energy level at level 0. N1, energy level at level 1. N2, energy level at level 2. N3, level 3. Now, you can see the values of the energy for each level. These are the values of energy for each level. Now, the question is, we should find the frequency of this electron that dropped from energy level 2 to energy level 0. So how do we solve this question quickly? Remember, we are given all the parameters H and C. So the energy of a given photon, a given particle is given by E is equal to HF. This is the energy of photon. Okay, where H is the Planck's constant and F is the frequency and E is the energy. So here, on this question, how do we find the energy? That is the change in the energy level now. Change in energy is equal to HF. And remember that this formula also is equal to HC all over lambda. Okay, that is when you make F subject of the formula. All right, so with this, we can solve. What will be the change in energy? It will be the drop from N2 down to N0. So we are going to find the change in these two. So that will be the bigger one minus the smaller one. That will be the change in the energy. So what's the value for N2? So our change in energy is going to be minus 2 electron volts minus, like we are minus, this should be E2 minus E1. That is higher energy level minus lower energy level, minus the 2. So minus 2, this value here, minus, then this second value here is minus 12. minus 12. That will be the change in energy. Is equal to, remember our H is 6.6 times 10 raised to the power minus 34. 6.6 times 10 raised to the power minus 34 times F. Our F is what we are looking for. So call it F. So minus 2 minus 10 will give us minus 2 plus 10. And minus 2 plus 10 is going to give us 8. So 8 is equal to 6.6 times 10 raised to the power minus 34 times F. So to find F, we divide both sides by the coefficient of F. 6.6 times 10 raised to the power minus 34 divided by 6.6 times 10 raised to the power minus 34. Cancel out. So F is equal to 8 divided by this. So which I will get my calculator. So work on this now is going to be 8 divided by, open bracket. I've said it before. Anytime you are making this kind of division and you have an index, a number that has raised to power as the denominator, you must put this in bracket when pressing your calculator. So 8 divided by, open bracket, 6.6 times 10 raised to power minus 34. Close brackets. That will give us 1.2. Oh, hold on. There's a mistake. Okay, that's 8 is an electron volt. Take note. Is an electron volt. So we're not going to work this way. No. Sorry about that. We're not going to work this way. So what are we going to do first? Our frequency should be in hertz. So our energy should be in joules. So we got, okay, so here is 8 electron volts, because this values here, this is 2 electron volts, this is 12 minus 12 electron volts. So is equal to 6.6 times 10 raised to the power minus 34 times F. Now we have to convert from electron volt to joule. According to the question, 1 electron volt, as you can see, is equal to 1.6 times 10 raised to the power minus 19. So if we have 8 electron volts, that should now be 8 times EV is 1.6 times 10 raised to the power minus 19. So is equal to 6.6 times 10 raised to the power minus 34 F. So divide both sides by 6.6 times 10 raised to the power minus 34 divided by 6.6 times 10 raised to the power minus 34. Cancel out our F here. We can now work it out with our calculator. So F will now be equal to 8 times 1.6 times 10 raised to power minus 19 divided by, open your brackets, 6.6 times 10 raised to power minus 34, close your bracket, and equal to. So this will be equal to 1.9 times 10, 1.94 times 10 raised to power 15 Hertz. This is going to be your answer for frequency. Please always remember to change it from that EV to joule. Take note. If not, it will remain in electron volt. And the electron volt cannot work with Hertz. So take note of that. Okay. Now, let's move to the second question. The second question says we should find the wavelength. So how do we get the wavelength of the emitted radiation? Now you remember, there's a relationship. Either you go back to this and use this formula, changing E is equal to HC all over lambda. Either you use this formula, where changing E will still give us 8 times 1.6 times 10 raised to the power minus 90 here, and our H giving C giving lambda. You've solved for lambda. Or you remember that from the wave, V is equal to F lambda. You can remember this formula? V is equal to F lambda. So the V here will represent the speed of light is equal to F times lambda. So which means our lambda, what are we looking for? Second one, lambda should be equal to C over F. Okay? So if we work on this now, we are going to have it at C over F. So lambda will be, our C is 3 times 10 raised to the power 8 divided by our F, which we have solved for, is 1.94 times 10 raised to the power minus 15. Minus 15. So when we work this out now with our calculator, work this out, we are going to have 3 times 10 raised to power 8 divided by bracket open 1.94 times 10 raised to power minus 15. Oh, not minus 15, it's 15. Raised to power 15 equal to, so this is going to give us that our wavelength finally is going to be 1.55 times 10 raised to power minus 7 meters. Remember, the unit of wavelength is meters. So you get, I hope this is clear. All right. The next question here says, a kinetic energy of 1.8 times 10 raised to power minus 18 joule is possessed by an electron ejected from the surface of a metal when the surface is illuminated with light. If the work function is 1.2 times 10 raised to power minus 18 joule, calculate the frequency of the incident photon. We are given C and we are given H. Okay, so solution. We can quickly list out our parameters. Energy, kinetic energy. Okay, let me use KE for kinetic energy. Kinetic energy KE was given as 1.8 times 10 raised to power minus 18. And we're given also a work function. Work function is that minimum work that is required to be done for an electron to be pulled from the surface of a metal. So this work function is equal to 1.2, especially when light is incident on that metal. 1.2 times 10 raised to the power minus 18 joule. This is one function. And they say we should calculate the frequency of the incident. We are giving H and the rest of them. So what are we going to do here? We are going to use the Einstein's equation of photoelectric effect or photoelectricity. What is photoelectricity? This is that phenomenon or that process whereby light falling on a surface will cause it to emit some electrons. So the emission of electron as a result of light being incident on metals is what we call photoelectric effect or photoelectricity. So that light will do two things on the body. One is pulling the electrons, two is accelerating the electrons off. So with that, let E represent the energy of the light, of the incident ray. When it falls on the metal, it will scoop out the electron from the surface. That energy required to remove that electron from the surface is called the work function, WO. Now, plus the second part of this energy will be used to move the electron off the surface. So, and when a body is moving, what type of energy is possessed by this body? Kinetic energy. So, plus kinetic energy. So, these two joined together will give us the energy of the light that is incident on it. And this energy is given by the formula HF. This one is given by the formula HFO. This WO is given by HFO, where FO here is different from F. F is the frequency of the incident radiation or incident light. Why FO is that what we call the threshold frequency. Threshold frequency. That frequency that must be surpassed or exceeded for an incident light to remove an electron from the surface. So for photoelectrons to be emitted or to be removed from the surface of metals, the incident ray must exceed, must be greater than the what? Than the threshold frequency. So that is what this FO is. So HF is equal to, because we are giving WO, which is this, we are giving kinetic energy, which is this, and they say we should find F. So that is why I had to break this energy down, is equal to WO plus KE, kinetic energy. So if we substitute, our H was given as 6.6 times 10 raised to power minus 34. So 6.6 times 10 raised to power minus 34 times F is equal to work function was given as 1.2 times 10 raised to power minus 18. Then plus kinetic energy. Kinetic energy is 1.8 times 10 raised to power minus 18. All right, so we're going to work this out. First, add this up now. To add this up, since they are in the same index, I'll just add the values together. So I'm going to have 1.2 plus 1.8, and that will give me 3. So the addition of these two will give us 6.6 times 10 raised to power minus 34 F is equal to 3 times 10 raised to power minus 18, because I'm adding. So just bring this out, keep it aside, factorize, and then add the remaining 2. They must be of the same value before you can factorize, before you can do this. All right? So next, to find our F, we'll divide both sides by the coefficient of F. So divide by 6.6 times 10 raised to power minus 34 divided by 6.6 times 10 raised to power minus 34. So cancel out. Our F now is equal to, so work it out with our calculator, 3 times 10 raised to power 18 divided by, open bracket, 6.6 times 10 raised to power minus 34, close bracket, equal to, so our answer here is going to be 4.55 times 10 raised to power 51 hertz. All right. So, and that will be your answer. Okay. Hello, wonderful people. On the screen here, we'll have a question that says, state two applications of electrical conduction through gases. Two applications of electrical conduction through gases. Okay, so before we answer this question, I want to ask a question. Is it possible for a gas to conduct electricity? Do you think gas can conduct electricity? And the answer is yes. The answer is yes. Solids, yes, currents or charges can flow through solids, same as in the liquids, as you can see during electrolysis. Then what about gas? Okay, on a normal condition of temperature and pressure, normal condition, that is the standard temperature and pressure, a gas is a non-conductor of electricity. Gas does not conduct electricity. But there is a situation, a gas, or condition gas can be placed and gas will be ionized, which will make it to accept the flow of charges, or the gas to be ionized into charges, so which will make current to start to flow, or electric charges flowing. And what condition is that? We have two conditions a gas will be placed, two conditions that will be necessary for gas to conduct electricity. One is that the gas will be placed in a vacuum and be connected to a high voltage source. So one condition is high voltage. And number two is low pressure. You need to lower the pressure of the gas and the container. So when you lower the pressure of the gas and you connect it to a high voltage source, what happens is that the gas in that particular vacuum, in that particular container, will be ionized. Ionizing means that it will be broken down into charges, both the positive and the negative charges. Now they will start flowing. This is how the cathode rays are being formed. When this gas is being ionized, then the negative charged particles of the gas will be attracted to the anode. The positive will be attracted to the cathode. Now, the negative that move towards the anode will go there and knock out, or the positive charges that move towards the cathode will go there and they knock off some charges, some electrons from the cathode or even from the anode. The negative, those charges that move towards the anode, can move to the anode and knock off some electrons. Like when they hit the anode and they knock off some electrons. So these electrons, they are what we call the cathode rays. So with this, gas can conduct electricity. So take note, low pressure and high voltage. Okay, now we're asked to state two applications of electrical conduction. And these are the applications of electrical conduction through gases. Number one, it can be used in the neon signs and advertising tubes. The neon signs, I believe you know what it means. Those signs that has some colorful lights, that we use to show things at night, and the advertising tubes can also be used in the fluorescent lamps. The fluorescent lamps that we use, fluorescent lamps, they are the kind of lamps that can produce light energy, or can give us light energy without being heated up. Okay, they can also be used in the sodium vapor and the mercury vapor lamps. And their knowledge of the application of electrical conduction through gases can also be used in the radio and television valves. So take note, you can choose two out of these. These are the applications of electrical conduction through gases. Okay, now the next question here They said the diagram below illustrates a cathode ray tube. Identify the components of X, Y, and Z. Okay? So we have to identify X. So what happens in a cathode ray tube? Remember, the cathode ray tube also, uses the phenomenon of thermionic emission, to produce some kind of light or replicate the image of an object on the screen. So what happens here is that this is the cathode. Okay, X represents the cathode. So here, this cathode is connected to a power supply. It's connected to a power supply. Okay, and this will make this is a heating element, or the cathode will be heated up. So when this cathode is heated up, what happens? Through a process known as thermionic emission, through this process, some electrons will be produced. What is thermionic emission? Thermionic emission is that phenomenon or that process by which metals will give off or release electrons when being heated. So when this metal here, this filament is heated up, then electrons will be emitted as a result of thermionic emission. Now, when they are released, they pass through a kind of slit. This slit is there to direct them, or to control, so that they don't just scatter. So it directs them, controls them towards this. This Y here represents the anode. And what is the work of the anode? Anode serves as an accelerator. The anode, due to these cathode rays, being negatively charged, because cathode rays, they are negatively charged. So these cathode rays, they are being attracted by this anode. Remember, the anode is the positive electrode of this setup. So the anode will pull them towards itself, so thereby making them to move faster. So they are now like fast-moving electrons. Now, on getting to this part, Z, they are called the deflectors. The deflectors, the X and Y deflectors, or X and Y deflecting plates. Either you call it deflector or you call it the deflecting plate. And what is the work of this deflector or the work of the deflecting plate? They help to channel or control those rays that have been produced, horizontally and vertically. The X deflector will control it horizontally, and the Y deflector will control the movement vertically, so that the rays can now be projected on this screen. So here is the screen. So normally you have some particles of gases here. Okay, and you know that this ray will, one of the properties of cathode rays is that they cause gases to glow. So when they touch these gases here, they will produce what? Light. They produce light on this screen, and this is how our old television works. So these are the parts of the cathode ray tube. The cathode here, the anode, the deflectors, and the screen. All right. So we move to the next question. The next question says, state one reason each why cathode rays are not electromagnetic waves. One, why are they not electromagnetic waves? Number two, state the reasons why they cast sharp shadows on objects in their path. Why they cast sharp shadows of objects in their paths. Why they can rotate in a light, sorry, they can rotate a light paddle wheel inside the discharge tube. Why? Okay, so just like I said before, sorry, a cathode ray I said before, a cathode ray, number one, the properties, okay, of cathode ray. Number one, we say that they are negatively charged. Number two, they move on a straight line, just like light. So, and when light is moving, or traveling on a straight line, if an object obstructs the path of light, what happens? There will be, that will lead to a formation of shadows. So cathode rays too, because they behave like light. Okay, let me start with number one that says, why they are not electromagnetic waves. Okay, so what are the characteristics or properties of electromagnetic waves? Number one, electromagnetic waves, they don't have mass and they are not charged. That is, they don't have a charge, electromagnetic waves. And electromagnetic waves, they cannot ionize gases or ionize particles when they come in contact with them because they don't have mass and they do not have charge. So because cathode rays have mass and is also charged, but behaves like light, but it also is a ray, but it has mass and it has charge. So because of that, it is not an electromagnetic waves. And remember the electromagnetic waves: radio, micro, infrared, visible spectrum, ultraviolet, X-ray, and gamma rays. These are electromagnetic waves. They do not have charge and they do not have mass. Okay. Even when light itself, which is visible spectrum, behave like a particle. Yes, it behaves like a particle, but it is not a particle because light does not have a mass. You can't get mass. You can't get light, like a quantity of light. No, light behaves like particle, yes, but light is not a particle. Okay, so A, the answer on I is that they have mass and charges. So that is why they are not electromagnetic waves. I. Why do they cast shadows of objects in their path? Just like I said, because they travel along a straight line. So if an object obstructs their path, they are going to cast a shadow, the same way light does. So the reason why they cast shadow, I, is because they travel on a straight line. They travel on a straight line, or you can say they are rectilinearly propagated. Okay, number three, why can these cathode rays rotate a light paddle inside of a discharge tube? Why? Now, think about it. Something like the air, if you get something like, let's say, a fan, standing fan, you keep it by the side, and you are standing by the fan, just look at, because I have a fan around me, and when the air coming from the fan is in contact with me, just as you can see right now, you notice that my cloth is moving. Okay? When you get an object, for example, this, you have an object, I have a piece of paper, and I'll have to okay, without pushing, it goes. It's because the air that I blew on it, the air has mass. That is why it can cause it to move. So same thing happens to cathode rays. When cathode rays they hit a light paddle. Paddle is just like something that, you know, can move. That when these rays, when they hit this paddle will start rotating, will start turning. So this because the reason is because they have mass, they have energy, they have momentum. So because of that, they can cause the light paddle to turn. So the reason is because they have mass, energy, and momentum. So this are the reasons why, why cathode rays, they are not electromagnetic waves. They cast shadows, sharp shadows of objects in their path and can rotate a light paddle well in a discharge tube. All right, so we'll move to the next question. The next question says, list two properties of cathode rays. Just like I've explained already, two properties of cathode rays. Number one, like I said, that they travel in a straight line. They move in a straight line. They are negatively charged particles. Remember, they are electrons that we are knocked out of the anode when the negative charged particles of the gas hit the anode and they knock out these electrons from the anode, making them to flow. And being attracted by the cathode made them to flow faster. And when they were flowing, these electrons are what we call the cathode rays. So they are deflected by electric fields. Yes, when they move closer to the field, to electric field, let's say electric field will have a positive and a negative charge. So if, for example, we have this positive and this negative, when the cathode rays move towards this, they don't continue moving on a straight line because they are negatively charged. You notice that this negative here will repel, will push it away, so making it to deflect towards the plus or the positive charge. Take note. So if this will be the electrons, when they get to this point, they will be repelled by negative. Remember that negative repels, while negative positive will attract. So they will be attracted by this positive, which will make them to deflect. They can produce fluorescence when they strike a certain materials. They cause some materials to glow when they strike them. They can ionize gas. When they come in contact with gas, that gas can conduct electricity. They can produce X-rays when they strike a metal target. When they hit some metal targets like tungsten, when they hit them, they can produce X-ray because X-rays are produced when a particular metal target or an obstruction is being hit by fast-moving electrons. All right. Okay. Stop here. All right, so the question we have here says, state two applications of electrolysis. State two applications of electrolysis. So you know what electrolysis is. Okay, the breaking down of electrolyte, the breaking down of that chemical reaction that will take place when current passes through a given electrolyte. That is called electrolysis. So that breakdown or decomposition of the electrolyte when current passes through it. So some masses of this, some masses will be deposited either at the anode or the cathode. Some masses, that deposition of masses or that dissociation or what we call decomposition of a solution, a particular solution known as electrolyte when current passes through it. That is what electrolysis is all about. Electrolysis or electrolytic cell. Electrolytic cell converts electrical energy into chemical energy. It is different from electric cell. Electrolytic cell is the cell that a setup where you have the anode, the cathode, connected, and the anode becomes the positive pole and the cathode the negative. And when current flows now, this electrolyte, this chemical, this solution here will be electrolyzed, or sorry, will be ionized, breaking down, will be broken down into ions. And these ions that will lead to a particular chemical. That breaking down is a kind of chemical reaction. So the electrical energy supplied here has been converted into chemical energy. But for electric cell, it is chemical reaction that will bring about what? Electricity to be generated. So they can ask you a question like this. The electrolytic cell converts electrical energy to chemical energy. Why electric cell converts chemical energy to electrical energy? So state two applications of state two applications of electrolysis. So number one is electroplating. Electroplating involves coating, coating a particular material to avoid corrosion or rusting. So we use a kind of sacrificial metal to coat one, okay, to coat some metals to avoid corrosion or rusting. So, and this can be done via electroplating. Chemistry students can attest to that, where you have the impure copper made purified by dissolving one sacrificial copper, so that the one that is to be electroplated, the one that is to be coated, the other one will dissolve and then migrate and coat the other one, okay, to prevent corrosion. It can also be used in electro-refining, or what we call purification of metals. You can use this to make impure coppers, for example, to be pure. It's also used in extraction of metals from their ore. Yes, we can use electrolysis to extract metals from their ores. Ore is O-R-E. The ores are the original form, that is not the purest form, but the original form of most of these metals. Something like iron that exists in hematite and so on. You know about the aluminum and the magnesium and so on. So they exist in their ores, in their oxides. So when they are being dug out from the crust, they are being subjected to extraction. And this extraction method involves electrolysis. Number four is the manufacture of chemicals. Yes, you can use this in the manufacture of hydrogen, manufacture of oxygen, manufacture of chlorine. Electrolysis method can be used. You can remember in the voltammeter is an electrolytical method, that is electrolysis of acidulated or acidified water. When we electrolyze acidified water, hydrogen and oxygen can be produced. So this can be used. This electrolysis can be used in the manufacture of chemicals. Then, okay, we also have another one that we can add here, very, very important. It can also be used in the calibration of ammeter. Electrolysis can be used in the calibration of ammeter. Calibration is like setting it to a particular standard. When you get the original value, a standard value, that you can now compare the error. Like you can from there get to know if your ammeter is not measuring correctly. Let's say it's giving you zero error and other form of errors. We can use electrolysis method to calibrate, to set a standard for the accurate value, to get the most accurate value of that particular measurement, that is the current from the ammeter. So take note of this: electroplating, purification of metals, extraction of metals, manufacture of chemicals, and calibration of ammeter. You can choose any two from this. So these are the uses or the applications of electrolysis. Number two says we should state two factors which affect the mass of element deposited during electrolysis. Remember I told you that elements, they are being deposited during electrolysis. And the factors that will affect this depends on, number one, the amount of current that is passed through. Remember that we pass current, and this current will break down or ionize the electrolyte, okay, and which some masses will now be deposited. So amount of electric current passed through the electrolyte, number one. Number two, the time for which the current flows will determine the mass that will be deposited. Number three, the electrochemical equivalent of the substance. So it depends on the chemical used. Each chemical, each electrolyte to be used will have what we call electrochemical equivalent. Okay, so this can also be determined by using this formula. Remember that M is equal to ZIT, where M is mass that will be deposited, Z is the electrochemical equivalent, is a constant, I is current, and T is time. So with this, you can remember what to write here. All right. The next question is a calculation question, and it says, a current of 2 ampere is passed through a copper voltameter. Voltameter is the instrument used for the investigation of electrolysis, most especially electrolysis of some liquids like acidified sulfuric acid. So the acidified water, okay? So a current of 2 ampere, list out a parameter just like I told you. Current I equal to 2 ampere, pass through a copper voltameter for 5 minutes, time 5 minutes, which you are going to convert to seconds. So from minute to seconds, 5 times 60. Remember that minute means 60 seconds. So multiply by 60, that will give us 300 seconds. If the electrochemical equivalent Z is 3.27 times 10 raised to the minus 7, this should be gram per coulomb or kilogram per coulomb. Determine the mass of the copper deposited. M is unknown. So, which formula are we to use? M is equal to ZIT. M is what we are looking for. Therefore, M is equal to, our Z is 3.27 times 10 raised to the minus 7 times I is 2, which is current, times T is 300. So when we multiply this, we are going to have 600 times, how did I get 600? 2 times 300, 600 times 3.27 times 10 raised to power minus 7. And that will be mass is equal to 0.000192, which I can write 1.96 times 10 raised to power 1, 2, 3, 4 minus 4 kilogram. So this is going to be our answer to this question. I hope it is easy. All right. The next question. The next question says, no. Okay, so the next question says, in an electrolysis experiment, the ammeter records a steady current of 1 ampere. The current recorded by the ammeter. Now, the mass of copper deposited in 30 minutes is 0.66 gram. Calculate the error in the ammeter reading if electrochemical equivalent of copper is 0.00033 gram per coulomb. Shall you see? I told you that we can use electrolysis to calibrate an ammeter. Now look at this ammeter measured a current of 1 ampere, which might not be so correct. So we need to use electrolysis method to get the actual value, to know if this 1 ampere is correct or not. So what are we going to do? Solution. Why is this thing disturbing me? Solution. These are the parameters. So take note that the current measured by the ammeter is 1 ampere. Keep it aside. Now let's use electrolysis method to find our own current and know if this is actually correct. If we get 1 ampere, it means that there is no error. But if we get a value that is bigger or smaller than this, it means that there is what? Error. And the value that, the one that we want to solve for now is the correct one. So we list out our parameters. Our time is 30 minutes, which is equal to 30 times, convert to seconds, times 60. Okay, is that 1,800? That's what it should be now. 1,800 seconds. Yes. Okay, now the mass, 0.66 gram. No, we are meant to convert. But when you open your eyes and you look, you notice that this electrochemical equivalent is in gram per coulomb. So there will be no need. So let's work with gram, okay? You convert when the units are not uniform. So once they are uniform, you just work that way. All right, so our mass is 0.66. What else? Calculate the error. It's error that we are looking for, but we need to find the correct value of current using electrolysis first. Is what we are looking for. And we are giving Z as 0.00033 gram per coulomb. So if you write our formula here should be M is equal to ZIT, ZIT, where our mass is 0.66 is equal to our Z is 0.00033 times our I is what we are looking for times T is 1,800. So which means 0.66 is equal to, multiply this out, we are going to have 0.00033 times 1,800, and that would be 0.594I. So you divide both sides by 0.594 divided by 0.594. So our I will be 0.66 divided by 0.594. Aha. Aha. I hope you can see what is about to happen here now. Our I is 1.11 ampere. Oh yeah. Compare yourself. Is there error? Is this value actually correct? So you see no. The value here, yes, very close, but there is an error. What will now be the error? The error, I believe you know, should now be 1.11 minus the measured value, which is 1, and that will give us 0.11 ampere. So this is the value of the error in the measurement. So this is one of the applications of electrolysis in the calibration of ammeter. Well done. All right. All right, the question we have here says that state the Faraday's law of electromagnetic induction. First of all, what is electromagnetic induction? From the word electro and magnetic and induction. Electro has to do with electric field or electrons. Magnetic field. Now, induction, production or sudden appearance, for something to appear as a result of interaction between the electric and magnetic field. So the electromagnetic induction simply means the production, or let me say, the production of voltage or current as a result of movement or relative movement between the electric field and the magnetic field. Whenever there is a relative movement, let's say this is the magnetic field and this is the electric field is moving across a magnetic field or turning within the magnetic field, or the magnetic field is permanent and the electric field is permanent and the magnetic field is moving around the electric field. Whenever there is a relative movement, either this one is not moving and the other one is moving, or this one is not moving and the other one is moving, that voltage will be produced or induced. So in electromagnetic induction is all about the production of voltage or EMF or current as a result of relative movement between an electric field or a conductor and what? A magnet. So state this law of Faraday's law of electromagnetic induction. We have basically two laws of electromagnetic induction. One is the Faraday's law and two is the Lenz's law. So let's see, statement of the Faraday's law. So the Faraday's law, it says that EMF, that is electromotive force, is always induced in a coil whenever there is a change in the magnetic flux around this conductor. And the magnitude of this induced EMF is proportional to the rate of change of this magnetic flux. Sorry, this is not showing clearly. Okay, let me break it down. That one, EMF or voltage is induced whenever there is a change in the magnetic flux. Now, what is magnetic flux? Magnetic flux represents those imaginary lines emanating from the north pole of a magnet towards the south of a magnet. Those lines that are coming that represent how the magnetic force acts. Those lines, collection of these lines is what we call magnetic flux. Now, whenever there is a kind of movement, when a conductor or a coil moves and causes a change in this magnetic flux, like we have lines here, and you have something that is rotating within this line, bringing about changes in this line, that voltage is always induced. So it says that voltage is induced in a conductor or in a coil whenever there is a change in the magnetic flux around this conductor. And now that the amount or the size of this voltage or the EMF that will be induced depends on the rate of change of this magnetic flux. I believe this is clear. So that EMF is induced whenever there is a change. And what to bring about this change is whenever there is a motion, a relative motion between a conductor and a magnetic field. If a conductor is rotating around a magnetic field, as you have in a generator, when you start your generator, you notice that there will be a movement first. And that movement occurs in a coil. So that coil is representing the electric field, and there's a magnet around this coil. So when there's a rotation of this coil in a magnet, it is cutting the magnetic field. It is bringing about variation or changes in the flux. And once this happens, that is why your generator will power your house. Electricity comes. So when there will be a movement force, this movement will cause magnetic field to change. And once this magnetic field changes or magnetic flux changes, voltage is induced according to Faraday's law. And that this voltage induced depends on the speed. In fact, it depends on the rate at which this magnetic field changes. I believe this is clear. All right. So we move to the next question. The next question says, list two factors which determine the magnitude of induced EMF. We have so many factors that will determine this magnitude. Remember that this magnitude depends on the rate of the change of this flux. Okay, so the factors that will affect this, number one, is the strength of the magnetic field or strength of the magnet. The strength of the magnetic field. I don't know why this is not showing very well. Why? So strength of the magnetic field, that is one. Number two, so the strength of the magnetic field, when you get a stronger magnet, you produce a stronger magnetic field. And the stronger the magnetic field, the stronger the EMF that will be produced, or the higher the EMF that will be produced. Two is the speed of relative motion between the coil and the magnet or the magnetic field. Between the coil and the magnetic field. Now that coil, it depends on how fast the coil is moving. If it is moving faster, then the voltage that will be produced or the EMF that will be induced is going to be higher. Number three is the number of turns in the coil, the number of turns of coil and wrapped around that particular conductor. So the number of turns, how many coils you have. So the more the number of coil, or the more the number of turns of this coil, the higher the EMF. Number four is the area of the coil. The area of the coil. The thicker or the bigger the coil is. A coil of this size and a coil of this size, this has more area. Therefore, this will produce more EMF than A. And number five is the angle of projection between the magnetic field and the coil. That is the angle of projection between the magnetic field of the coil. In fact, to remember all of this, there's a formula you need to know. First, remember that the EMF depends on or is equal to N A B W sine or omega sine theta, where N here is the number of turns. This A is area, E is magnetic flux density, you know that already, or the strength of the magnetic field. W here is angular velocity, or angular frequency, or angular speed. And this theta is the angle between the magnetic field and the electric field. I believe this is clear. All right, so we move to the next question. It says, the coil of an electric generator has 500 turns and 8 centimeter diameter. If it rotates in a magnetic field of density 0.25 Tesla, calculate the angular speed when its peak voltage is 480 volts. And we are given pi as 3.142. A solution. whenever you are given a question in WAEC, first thing you do will be to list out your parameters. So when you list out your parameters, next is to write your formula. After writing your formula, then you substitute, solve, and you get your answer. Do the necessary conversions needed too before you start solving. All right. So the coil has 500 tons. So tons, that is a number of tons, just like we discussed now. N is 500 tons. And we have diameter G as 8.0 centimeters. Why this diameter? This diameter will help us to find area because, you know, G in centimeters, we convert this to meters, so which is 8 all over 100, which is equal to 0.08 meters. If it rotates in a magnetic field density, so we have the B at 0.25. Calculate the angular velocity or angular speed. We are looking for omega. And the voltage, peak voltage, maximum voltage is our E is the voltage. E there is the EMF, which is voltage, is equal to 480 volts. And pi is 3.142. So looking at these parameters, you notice something. These look similar to what we just discussed now about the factors that will affect the EMF induced in an electromagnetic field or during electromagnetic induction. And we have it that E is equal to NABW sine theta. Okay? But because they use the word peak voltage, another word for peak is maximum. So, and it is maximum whenever you hear electromagnetic field or electric and magnetic field, a conductor and a magnet, just know that the angle, they must be, if they are perpendicular, it means that the value of whatever thing we are talking about is maximum. Okay? The force is maximum, the voltage induced is maximum when the angle is 90. But if they are parallel, the force is 0, the voltage is 0, is minimum. Okay? So because they said peak voltage, it means that our theta is 90 already. So our formula here is going to be E equal to NABW. Sine 90 is 1. Okay, so N was given, A, we need to find A. And remember that area is equal to pi r squared. We are talking about wire here, and wire is cylindrical in nature. And area of a cylinder is pi r squared. It's same as the area of a circle. Okay, so pi r squared, we're going to use it. Now we don't have the radius, and you can remember that radius is equal to diameter divided by 2. So when you divide this by 2, you get the radius, then you input the radius here and find the area. That is 1. But someone can, anytime you are given a diameter, you can go straight without doing this by using this formula for area. Area is equal to pi d squared over 4. If you use this, you can solve. If you are given diameter, straight, use this formula. If you are given radius, use this formula. Okay, so our area is going to be pi is 3.142 times our diameter is 0.08 squared divided by 4. If we work this out, we are going to have 0.08 times 0.08, that's 0.08 squared, times 3.142 is equal to divided by 4. That will give us 0.0055. Let me stop here. 5 meters squared. Okay, now that we have gotten our area, can we now solve for the EMF that we are looking for? What are we looking for? We are looking for, okay, angular speed. So from here, can we say, since E is equal to NABW, it means that W is equal to E all over NAB, yes. So our W or omega is equal to, our E is 480 divided by our N is 500 times our A is 0.005, then times our B is 0.25. So angular velocity, we'll work this in our calculator. We are going to have 480 divided by, open bracket, 500 times 0.005 times 0.25, close bracket, equal to. So we are going to have 768 radians per second. This is the unit of angular velocity, radians per second. So this is going to be our final answer. All right. Now, on the next say, we should define inductance. Define inductance. Okay? Remember that I've said what induce, something generation, when you generate voltage or when you generate current as a result of change in the flux, right? When current will flow through a magnetic field or when a conductor is moving in a magnetic field, there will be a change in the flux, causing voltage to be induced. Voltage will just appear, because of this action. So what is inductance as it relates to electromagnetic force or as it relates to transformers and so on? So inductance simply means the phenomenon in which a changing current in one coil will produce a changing magnetic field that induces EMF in another nearby coil. That mutual inductance, mutual, like, mutual now when they say, this is a mutual conversation, like you and I, mutual conversation. When current that will cause, my own field to change, and because of change in the magnetic field of this particular conductor now, I will cause voltage to be induced. You understand? The next person, that is, the voltage will be induced or will cause another field or another coil. Let's say I'm a coil, you, another coil. We are mutual, we are close to each other. So because current entered here and will cause my field to change, let's say there will be a mechanical movement, which that movement will cause a change in the flux of my particular field, in my coil. Okay, you understand? So this change in this particular coil will, because we are close to each other, will cause your own coil or your own field flux to start changing, which will make voltage to be induced. In fact, voltage induced in a particular body, causing voltage to be induced in a nearby body. I don't know if this is clear. So the phenomenon in which a changing current in one coil produces a changing magnetic field that induces an EMF in another nearby coil. Or the process by which EMF is induced in one coil when current flowing in a nearby coil changes. When something that is happening in one coil is affecting another one, current enters here that will cause the flux to change, and this will now induce voltage into the second coil now, because they are nearby, because they are mutual. That is what mutual inductance is all about. So the process by which an EMF is induced in one coil when the current flowing in a nearby coil changes, or the phenomenon in which a changing current in one coil will produce a changing magnetic field that induces voltage or EMF in a nearby coil. That is mutual inductance. Thank you. Hello. The question we have on the screen here says that a wire of length 10 centimeters carrying a current of 4 ampere is placed between the poles of a powerful electromagnet of electromagnetic flux density 2.0 Tesla. Calculate the number one, the force of the wire when it is parallel to the field. Number two, the force on the wire when it makes an angle of 60 degrees with the field. Okay, so this question is about the force acting on a given conductor. Okay, so to list out the parameters here, we have the length, L, equal to 10 centimeters, which we are going to convert to meters by dividing by 100. So we're going to have 10 divided by 100, which is equal to 0.1 meters. Then current I equal to 4 amp. And magnetic flux density B is equal to 2 Tesla. Now calculate the force when it is parallel. Now, when the wire is parallel to the magnetic field, you know, it means when two parallel lines has no angle between them. So when parallel, it means that the angle between the two fields is 0. Okay? So, and the relationship, the formula that connects the force on a given conductor, the magnetic flux density or the strength of the magnetic field, and the current and the length of a conductor is given by the formula F is equal to BIL sine theta. F is equal to BIL sine theta. So this is the formula that connects the strength of a magnetic field, the current, the length of a conductor. And you know that whenever a current carrying conductor is placed in a magnetic field, a mechanical motion is always noticed. And this motion is caused by a force, and this should be the force. So the force is what they say we should find. So when theta is 0, we are going to have F is equal to BIL, times sine 0. And sine 0 is 0. And 0 multiply everything here will still give us 0. So the force when the two fields are parallel to each other is equal to 0. All right. So secondly, the force on the wire when it makes an angle of 60 degrees. So when theta is equal to 60 degrees, our formula will still be F is equal to BIL sine theta. So F is what we are looking for. F is equal to B is 2 multiplied by I is current multiplied by L is the length, 0.1, which if we times 2 times 4, 8 times 0.1 will give us 0.8 Newton. So this is going to be the force when the angle is 60 degrees. They can as well ask you to find the maximum force. They can ask you to find the maximum force. So the maximum force, this force is maximum when theta is 90 degrees, when they are perpendicular to each other. And when this happens, it means that F is equal to BIL sine 90. And sine 90 is 1, so which will give us F equal to BIL only, which you substitute, you can now find the force. All right. So we move to the next question. The next question says, an electron enters perpendicularly into a uniform magnetic field, which has a flux density of 0.12 Tesla. This results in a magnetic force of 9.6 times 10 raised to the power minus 12 Newton on the electron. Now, calculate the speed of the electron as it enters the magnetic field. Okay, that should be field. So solution, and we are given the charge of electron, the quantity of charge of electron, 1.6 times 10 raised to the power minus 19 coulomb. So to solve this question is still about the force in a magnetic field. And if we list out our parameters, we're given first the magnetic flux density B is equal to 0.12 Tesla. Then we are given a force F as 9.6 times 10 raised to the power minus 12. And they say we should calculate the speed of the electron. Speed is V. Let me use V, velocity. Speed of the electron is what I'm looking for. If the charge of electron, or the quantity of charge of electron, let me use Q, is equal to 1.6 times 10 raised to the power minus 19 coulomb. Okay? And remember they said that it entered perpendicularly. The electron entered perpendicularly into this magnetic field. So if the magnetic field is perpendicular to the electric field created by the movement of this electron, you are going to have it that F, like I told you, is BIL sine theta, be our formula. But the formula also can be, this is in terms of the length of a conductor, the current, and the strength of the magnetic field. But when it comes to, in terms of charge, the velocity of the electron, the formula becomes F is equal to QVB sine theta, where Q is the quantity of the charge, V is the velocity or the speed, and B is the magnetic flux density or the strength of the magnetic field. So if it enters perpendicularly, it means that theta is equal to 90. That means that the force is going to be maximum. So what we are looking for now will be F is equal to, our Q is 1.6 times. Are we looking for F? No, we are looking for the speed, okay? So since we are looking for the speed, so our F was giving us this. So F here, I'll write 9.6 times 10 raised to the power minus 12 is equal to Q. Q is 1.6 times 10 raised to the power minus 19 times V is what we are looking for. Then times B is 0.12 Tesla, then times sine 90. Sine theta should be sine 90. Now, if we multiply, sine 90 will give us 1. So we are going to have 9.6 times 10 raised to the power minus 12 is equal to 1.6 times 10 raised to the power minus 19 times 0.12. So when we do this, let me get my calculator. Okay, so we're going to have 0.12 times 1.6, and that would be 0.192. So this is going to give us 1.92 times 10 raised to the power minus 20. Okay? Then times V. So we divide both sides by 1.92 times 10 raised to the power minus 20. Divide here by 1.92 times 10 raised to the power minus 20. This cancels this. Now our V becomes 9.6 times 10 raised to the power minus 12 divided by 1.92 times 10 raised to the power minus 20. I can just quickly work this out and then do this. So 9.6 divided by 1.92. That will be 5. Then times 10 raised to the power minus 12. We can use this indices. 10 raised to the power minus 12. Now divided by 10 raised to the power minus 20 will be 10 raised to the power minus 12 minus 20. That will be 10 raised to the power minus 12 plus 20 will give us 8. So our answer will be 5 times 10 raised to the power 8 meters per second is equal to V. So this is going to be our final answer. You get? All right. So we move to the next question. All right. So the next question says, an electron moves with a speed of 2 times 10 raised to the power 7 meters per second in an orbit. Please take note of this orbit. Okay? In an orbit, in a uniform magnetic field of 1.2 times 10 raised to the power minus 3 Tesla. Calculate the radius of the orbit. We are given mass of an electron as 9.11 times 10 raised to the power minus 31 kilogram, and charge on an electron as 1.61 times 10 raised to the power minus 19 coulombs. So to solve, first we list out our parameters. One, we have a speed, V is equal to 2 times 10 raised to the power 7. What else do we have here? We have an orbit. In an orbit, take note that the orbit is circular. Take note of this. So with the magnetic flux density B as 1.2 times 10 raised to the power minus 3 Tesla. Once you see Tesla, just know that it represents the magnetic flux density. It is also known as strength of magnetic field. Okay? Calculate the radius of the orbit. So we are looking for R, radius of the orbit, and the mass of the electron. The mass of the electron was given as 9.11 times 10 raised to the power minus 31. And the charge on an electron, charge Q, is equal to 1.61 times 10 raised to the power minus 19 coulomb. Okay, so remember our formula when it comes to force on a given charge in electrical conductor that is placed in a magnetic field. You remember that F is equal to QVB sine theta. Yes, but when we talk about the maximum force on it, that force is equal to QVB. That is, the theta is 90, and sine 90 will give us 1. So the maximum force acting on this is QVB. And when, let's say that the conductor is circular, and this charge is to move around this orbit, the force that is in charge, making an object to move around a circular path that is acting towards the center of that circle, is what we call the centripetal force. And the centripetal force is given by mv squared all over r. So this force is the force acting on this particular charge. When the electron enters a magnetic field, the electron will start moving. There is a force that will make it to start moving. That force is equal to this. And now, if this movement is circular, it means that this force also is centripetal. I don't know if you get. So this force also is making it to move around, and it is centripetal. So it therefore means that the centripetal force is the same as the force acting on the charge in a magnetic field. Okay, so with this, we can say that QVB is equal to mv squared all over r. Okay, so with this, I think V here can cancel one of this V, leaving us with QV is equal to mv all over r. And we are looking for r. So from here, we can make r subject of the formula, cross multiply. We are going to have QBr is equal to mv. And divide both sides by QB. To make r subject of the formula, r becomes mv all over qb. So we substitute our values. So our r is equal to, the mass is given by 9.11 times 10 raised to the power minus 31 times our v is 2 times 10 raised to the power 7 meters per second, divided by our Q is 1.61 times 10 raised to the power minus 19 times our B is 1.2 times 10 raised to the power minus 3. So we need to work this out. So our R now is equal to, we work this out, we are going to have okay, okay, so we have 9.11 times 10 raised to power minus 31 minus, oh, no, 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 no. 9.11 times 10 raised to power minus 31 times 2 times 10 raised to power 7 equal to. So this will give us 1.822 times 10 raised to power minus 23 divided by, down here we'll have 1.61 times 10 raised to power minus 19 times 1.2 times 10 raised to power, that minus 3? Minus 3. And that will give us 1.932 times 10 raised to power minus 22. So when we work this out, we are going to have 1.822 times 10 raised to power minus 23 divided by, open bracket, 1.932, oh, 1.932 times 10 raised to power minus 22, close bracket. That will give us R as 0.094 meters. And that will be the answer to this particular question. I believe this is well understood. All right. So we move to the next question. So the next question says, the diagram below illustrates an arrangement of cathode ray from an electron gun and a bar magnet placed perpendicular to the direction of the ray. Sorry? The diagram below illustrates the diagram below illustrates an arrangement of a cathode ray from an electron gun and a bar magnet placed perpendicularly to the direction of the ray. Will the ray bend downward or upward? Explain. Okay, so we have a diagram. Look at the diagram here. And this is an electron gun that will shoot out cathode ray. Now this cathode ray moved and will now have a magnet placed here, which will produce a magnetic field. Okay? Sorry, please. Okay. So, as I was saying, the electron gun shoots out the cathode ray, and we all know that the cathode ray is negatively charged, one of the properties of cathode rays. So this cathode ray, on getting to a magnetic field, you know that the magnetic field for the magnetic line of force along the south, the arrows are always moving in here for the south, and you know that the south is just like what's it called? The negative of negative terminal of electric charge. So when this cathode ray is released and it gets towards this magnetic pole, it is such that this pole will always push away this ray, like using the Fleming's left-hand rule. Okay, you know that the magnetic field always acts perpendicular to the what? To the electric field. So this cathode ray is like a charge, a negative charge, electron that is coming closer here. So there will be a kind of repulsion between this south and this what? Electric field, or the electric pole, sorry, the magnetic pole, sorry, will act perpendicular to what? To the electric what? Charge, or that charge that is coming up. So this will repel this charge that will make this line not to continue moving straight, but to curve outward. Okay, from this field. So remember that this charge is this way. So when the cathode ray is being released and it gets to this magnetic field, it's going to be repelled by this south. It's going to be repelled by the south pole. So it is going to bend upward. That will be the answer. Upward is going to be the answer. Now, explain. So how do we explain this? So we can say that the magnetic field always acts perpendicularly to the electric field. The magnetic field will repel the cathode ray, thereby making it to move upward or outward. Thereby making it to move upward or outward. So this is the explanation you are going to give. This is negatively charged. On getting here will be repelled because if this will be the electric field, this is going to be the magnetic field. And this is going to be the final movement of the electric field or the resultant field here. So it's going to deflect away. All right. I hope it is clear. So we move to the next question. All right. So the question we have here says we have an equation, a nuclear equation, A with mass number 23, atomic number 11 plus B, mass number 2, atomic number 1, to give out C, mass, atomic number P and Q plus proton. Then P, Q, that is for C, will also give E plus beta. Now they said a nucleus C formed artificially from A and B is radioactive and quickly decays to another nucleus, E, as indicated in the nuclear equations above. Now determine the values of P, Q, R, and S. Okay, so quickly, without wasting much time to solve this question solution, you need to write out the nuclear equation. First, we have A having mass number 23 and 11. A should be sodium if you are a good chemistry student, you should know. Okay, A plus B, 2 and 1. Okay, this should be a deuterium. Yes, a deuterium. This is a deuterium. A deuterium has atomic number of 1. Deuterium, an isotope of hydrogen. So to give out C, G, Q plus proton. Like I told you, the isotopes of hydrogen, there are 3. One is called proton. And proton is hydrogen 1, 1. That is mass number of 1 and atomic number of 1. What is an isotope? Isotope is group of element or 2 or more elements that will have the same atomic number but different mass numbers. Okay? Atoms of the same element with the same proton number or atomic number and different nucleon number or mass number. So proton is hydrogen 1,1, deuterium is hydrogen 2,1. Notice the mass number is always 1, the atomic number is always 1. And then the tritium is hydrogen 3,1. So when they say proton, so what you're supposed to write here, proton in place of proton is hydrogen 1,1. Now, to find this Q, we need to balance the equation. Just take note that mass number of the reactant should be equal to the mass number of the product. Which one are the mass number? This 23, this 2, this P, and this 1. So which means 23 plus 2 is equal to P plus 1. 23 plus 2 will give us 25 is equal to P plus 1. Make P subject of the formula. P is equal to 25 minus 1. That will give us 24. So P is equal to 24. We've gotten our P. Okay, so how do we find the Q? Q is down. So remember also the same thing. The atomic number of the reactant should be equal to the atomic number of the product. So this should be equal to this. So with this, we can now write also that 11 plus 1 is equal to Q plus 1. This plus this is equal to this plus this. So that will give us 12 is equal to Q plus 1. Therefore, Q is equal to 12 minus 1. Q is 11. So 24, 11. So the element C, which is 24, 11, you can guess which element should be this. Having a proton number of 11 should tell you that this is still a sodium, but an isotope of what? Sodium. You can see that we have sodium 1123 and sodium 1124. So it's an isotope of sodium. All right. Now they say we should find also R and S. So you can see that this C produced here now is a radioactive element. So it has to decay again to produce E. So we need to write the equation again that C, P, Q give out E of mass number R and atomic number of S plus beta. Beta. So how do we represent beta? Just know that a beta particle represents what? An electron. So it represents an electron. How do we represent electron? Electron is E minus 1. Sorry. E0 and minus 1. Electron is 0 and minus 1. This is an electron, which is what? A beta particle. So take note. This is something as beta. We also have the alpha. Alpha. So quickly, the alpha particle represents helium. I've said this before. Of 4 and 2. This is an alpha particle. All right. So what am I going to write in place of beta here? I'm going to write electron 0 minus 1. So what am I going to do next? We balance. Remember that the summation of the mass number of the reactant is equal to that of the product. Reactant to have only 1. Product to have 1, 2. So what do we have now? P is equal to R plus 0. So P is equal to we have a value for P now and Q. Sorry about that. We have a value for P and Q. So since we've gotten our value, what's the value? For C now, C here should equal to 24 and Q here should equal to 11 from this solving, from what we solved here. So it's C 24, 11 from our solving. So P is equal to 24. So we can now solve 24 is equal to R plus 0. So 24 is equal to R plus 0 will give us R. Therefore, R is equal to 24. Then next, this is equal to this plus this. So if we work it out, we are going to have it that 11 is equal to S plus minus 1. Remember, we're adding this plus this will give us this. So plus minus. So 11 is equal to S plus minus is minus 1. So S is equal to 11 plus 1, which will give us 12. Therefore, E, the product E, has a mass number of 24, that is R, and the other of 12. If they ask you, because I know physics will not ask you about the name of the element, but chemistry will do. So if you have this kind of a thing, which element do you think is this? You locate it by the atomic number. So the element with the atomic number of 12 is magnesium. So that shows that E is magnesium. Hope you get. All right. Now the next question here, it says two nuclear equations below. Look at the first one, equation A, and the second one, equation B.